How's everyone doing? Merry Christmas to everyone that celebrates. I am not one of those people that celebrates, and typically today I would be out snowboarding, but COVID-19 had other plans for me this year. Instead, I think that we'll probably just hopefully solve the challenge we were working on yesterday, the day before, whichever day it was, um, and see if we could unlock this lock. Um, I'm gonna go ahead and get logged into microcorruption and get us to a point where I can flip over back to my screen. I I don't know if any of you have seen like the papers and like research coming out about being able to like detect like effectively like key logging based on the audio of key presses. And I've realized that like I always like log in on stream, and I know I don't like have it on like you can't see what I'm typing or anything like that. But I mean it's clear how many characters my password is. I'm curious like how well that stuff works and if that's like a real like side channel type thing that could happen, uh, where someone would be able to actually figure out the password. Um, I mean, I guess because it's the password manager, like I probably would never know because they'd have to basically like break into the password manager or my computer to get the vault before they could like use it. But I'm genuinely kind of curious like how real of a threat that is, and like whether or not that's something that like you'd have to be concerned about on stream if someone really wanted to hack you. So I'm gonna pop open the. First of all, let's make sure the audio is good. It looks like it's coming through all right. I can see a little green bars right here. Uh, we're not clipping. We're not in the red. That's the ideal spot. I'm gonna pop open my terminal, and we're gonna get into Linux, or at least as close to Linux as we can. Uh, Now, for anyone who's not aware of where we are today from yesterday, we are working on this CTF. We've been doing it for the past couple weeks now. It's called Microcorruption. Basically, it provides a simulated lock uh, with various security controls, and our job is to break that smart lock. The microcontroller that runs it is a virtualized MSP430, which is a microcontroller from TI using the name like MSP430 instruction set. It's a RISC architecture, very small instruction set, very simple. Basically, the interface that we get is this. I'm gonna switch over to middle mode, but this is effectively a debugger that we're attached to debug the individual lock. We have our disassembly here. This is our memory view. This is our interface to deal with the debugger. Registers. This is the current instruction being executed, and this is our input and output view right here. Before I do this, though, I'm going to do one thing, which is open up the lock manual and the assembler, because I probably will need those. We're pretty far into this now. Like I think there's maybe like 4 or 5 challenges left. They start off pretty easy, and then they get I don't know if I'd call these like really difficult, but they're pretty like reasonably hard if you don't have experience doing this sort of thing. This is intended to be like an introductory game, but I mean it really does take you from like basically nothing to defeating a lot of like the common mechanisms you might see today. So this challenge specifically has ASLR, or address space layout randomization, which is when the code itself is mapped into random locations on every execution or kind of runs, whatever the constraints are for that implementation. In this one, as part of the startup process, it actually does the remapping. And so because of that, we can't just like consistently say, oh yeah, my shell code is always going to run at this location, or this ROP gadget that I'm using is always going to be at this location. And if you don't know what any of that means, don't worry, we'll get to that shortly. But yesterday we found our ASLR bypass, which was pretty straightforward. I also have this in Binary Ninja, so that we have an easy way to... oh, come on. I definitely saved this. What are you doing? Don't give me that shit. Literally did this yesterday. Like this is... We are good. Like, I 100% saved this. I'm gonna be so pissed if this is gone. No, I was clicking the wrong one. Error reading database global key current not found. Error reading database. What the fuck does this mean? Yo, this is really not cool. This is like some IDA shit where it just like fuck you, I'm not doing this anymore. Yeah, this is not helpful whatsoever. Great. Real nice. Global key current not found. I don't know what this means. I'm guessing we're probably not going to get any sort of support on Christmas for this. But I will definitely be asking about this later. Oh, fuck. I hope it didn't overwrite this. I bet what happened is I opened up the file and it created a new database and it overwrote the old one and I lost it. Because our last modified time is here. The C time is correct. I don't have restore points or anything like this. This is fucking garbage. Really? This is what you're gonna fucking do? So... Fuck off. No, how do I stop this? I literally don't want you to open it. I don't want you to open it. Great. So we lost everything. That's not a big deal. Like we can redo. We can redo this. I am so pissed though that's what that does. Let's see how much of it actually is fucked, and it's pretty much all of it. Yeah. So, I mean, I guess we don't necessarily need this. God damn it. So, I guess where do I start? Let's go back to the challenge and let's start there. We're gonna start this continue, and we see that this is running, and it's going to break at the first point it wants input from. We also see that all this gets overwritten. Now, what the challenge is doing, and what we figured out yesterday or the day before, or whenever it was, that if we look at mean, it basically takes a random number here, and then it does some math, and that becomes the new point. It then mem copies 4K starting from 4400, which is the beginning here. This has to be right here, and I'll explain in a minute why. But it basically starts copying from here all the way through the end of the data here, and it copies it to the new address that it randomly selects and does some math to. The second rand that we see there is used to generate the new stack, because there's some stack init stuff because it needs the stack to start with, but it moves the stack and the rest of Flash to some other location. So all of this breaks, and we don't actually know where it is. What we did find, though, is that there's a format string vulnerability that exists within this program. So I'm going to call it reset and then run this. And we did some very rudimentary checking. Basically, we figured out that we get, I think it's 8 bytes of input right here. It just tells us it's 8 chars, and I verified that we can't write more than 8 characters. But what we can do is we can leak an address. So we're gonna send this. I'm gonna hit finish, and we see 4 bytes here. That's the first X. 4 bytes here. That's the second X. And what this is leaking is a reliable address on the stack. If you don't really understand why this is working, I have talked a little bit about format string vulnerabilities in a previous part of this. All those videos are on Twitch and YouTube. And if you have questions, ask them in chat, and I can explain. But I'm not going to go jump and go over all that. We have this leak. We found out yesterday that it reliably leaks us to 874 bytes into Flash. So this address is, if we imagine that Flash starts at 4400 hex, because that's where it did originally, this would be 874 bytes in every single time. So what we can do is we can subtract 874 from this address, and then we know exactly where the beginning of the Flash is. So I'm going to pop open another terminal here, and do we have RBEnv installed? We don't have RBEnv installed. Where did we get Ruby from? One of the other things that happened today is that Ruby 3 got released. Upgrade. Let's see if we can get Ruby 3. I haven't actually used it yet, and it is apparently pretty nice, and there's some new stuff on it. So let's see if it's made its way into Ubuntu. It has not. All right. Not super important. Anyway, 90C6 minus 874. And I believe it's decimal 874, not hex. Let's see here. Oops. And then the other piece that I need here is I need to turn this into a hex value. So this is the beginning of Flash. And this is garbage. All my symbols are missing because I lost that. I lost the database. So we might have to just go in and redo this. I know this isn't the most interesting or exciting part, but we might just have to do this. I don't want the graph view. This is also like one of the most annoying things about Binary Ninja is that it will go and switch back to the wrong view that I don't want. I think we saw yesterday there were some options around that. Where was that? Preferences. That's interesting. Oh, maybe we don't want that. Let's just stick with dark. So default disassembly graph, default linear type. I don't know. I mean, I just want to stick with like the one that it is, and that's the most annoying part. Is it doesn't do that. So I'm sorry, this is gonna be like the least interesting part. But I need to go back in and redo all this so I have actual like function boundaries. And this is gonna be super, super frustrating. And this is that same bug we ran into yesterday where it great. I think that might be the problem, is that it's confused here. I want to make this basically not a procedure. Undefined current function. Yeah, and I can't do it from in here, which is like the other really irritating thing is even though I know like where it is, I can't go and just hit P. So I'm right here, I'm gonna hit P and oops, I don't know what I just changed, but that's not what I wanted to do. So that's set correct. We're gonna name these init stack after the bis. This ends up being low level init. The other thing I explained yesterday is that sometimes we're going to see differences between what we see here and what we see here. The reasoning for that is not that the disassembly here is wrong. It's that MSP 430 has this concept of emulated instructions. For instance, CLR, which is clear, it just zeroes out a register. The opcodes are mapped to a move instruction, but semantically, like moving 0 into a register is clearing it. So the better MSP 430 disassemblers are smarter, and they know like, oh, this is a clear operation because the value here is 0. Is there a dog under the door there? But yeah, the one that we're using here unfortunately doesn't know all those things. You might end up building a better one that does. Let's see. Move 32. This is the next one there. That's so this is do copy data. can't believe we have to redo this. This is such garbage. So do copy data. GNZ. This goes down to here. Guess at least I can hit escape and it'll bring us back. Do clear BSS. And then this ends at 4476. This is stop prog exec. It's weird that it knows though. Like the like some of the stuff is still here. Like it knows that like what I'm completing, and I'm not sure why it knows that. But that is super frustrating. That's a procedure. This is CTOR's end. Yeah, like all these are still there. This is ASLR main, and it ends at. Is it underscore ASLR main or is it ASLR main? This is underscore ASLR main. Uh, 475C. So it ended at the right place. This is ASLR main. So you remember some of it, but you don't remember all of it. That's real cool. This is gonna be a massive function. Ends at 48EC. Which is the right spot. This is int, or no, it's underscore int. The next one is int. This is put char. Get char. So the first thing I'm going to do once I'm done here is I'm going to back this up so we have a copy that isn't fucked, and then verify that it works. Get string. This is puts. Mem copies at 49E8. B0. This is rand. Conditional unlock door. Yeah, see, it remembers all the names. It it just doesn't have the data. And then this last one is unexpected. Great. All right, so let's save this. We're gonna call this stuff. Yes, I want to replace it. All right, so now the first thing I'm gonna do is I'm gonna go back to here and I'm gonna copy this and I'm gonna paste it and we're gonna open this up. All right. So we're set. This is all usable. Great. So don't need that. We have our copy. The reason I'm doing all this is because we need to do some searching for some gadgets, most likely. We're going to redo what I was doing here. So we're going to hit reset. And I'm going to show how this workflow works. So I'm continuing. It takes a little while to do all this moving around. I'm going to leak our address. Hit finish. This prints it. BF12. This is our address. So I'm going to go into here. I'm going to update this. And this is our new base address for the flash. I'm going to go to rebase and I'm going to rebase this thing. And all this is doing is saying take the beginning address that we have right now, which is 4400, and instead make that this. So everything shifts however much the difference is from 4400 to this. So I'm going to hit that. Everything's going to get like rejiggered around and move this back to disassembly. Super frustrating that it can't remember like what my view is, but you know what? Maybe there's an option that I'm just not smart enough to figure out. So now the benefit to doing this is that all of these addresses are now correct. And what we did yesterday was we had the ability to overwrite the return address on the stack. So we can take control flow here. We can see that by moving here. I'm going to do hex encoded here. What we found was that it takes us, I think it's 8 bytes to get to the return address. We can write a total of 20. So 1, 2, 3, 4, 5, 6, 7, 8. And then the next 2 bytes are going to be our return address. So we can return to anywhere, but we need to know the right addresses. And now we have the right addresses. I am going to pick somewhere that we can like do something like maybe useful. I'm so curious like what this does. I don't understand what that is, but like maybe it's helpful. Anyway, let's pick somewhere like useful. We'll do like a rock knob. Or here, we'll just do a call. 0ABF. So 0ABF. I'm gonna go back to here and we'll do 1, 2, 3, 4, 5, 6, 7, 8, 0ABF. So I'm gonna hit send. We're gonna hit finish, and it tells us we're wrong. But if you look here, PC is now at BF0A, which is call 14. Now, so we've managed to get control flow. So we know that we can take control. We can start doing whatever we are going to do. Now the problem is that we don't really have a good way to like do anything yet. Our stack is read write execute, but we don't know where our stack is. So theoretically, we could put shellcode on it. I've already written some shellcode that we have in here. Maybe I don't have it written in here, but basically it's right here. And basically, what this does is it is to move 7F00 into R2 and call 10. And the reason we're doing this specific stuff is in here. So it tells us about where are the interrupts? There's like a software interrupts section. Yeah, that's it, right there. Software interrupts. The lock it all has extended the MSP430 to support software interrupts, implemented with a call gate at address hex 10. And I said it was really important that the hex 10 was the beginning of... That's not what I wanted. Here. This, right here, this part never moved. We didn't relocate this specific part because that is something that is built into this specific chip, and if that moved, the interrupts would not work. So this part doesn't get relocated, and we know for sure that we can do this. And so the way that these interrupts work is when the CPU executes the instructions at this address, which in this case is just a return, so it's not doing anything. Begins executing special purpose lock at all prod to perform special purpose functions such as printing characters to the console or requesting terminal input. The interrupt kind is passed in R2, the status register, on the high byte. Typically, the status register R2, also known as SR, right here. So this is SR or R2. I believe that only the low bytes are used for status flags. The high ones are not. And so what they've done is they've repurposed the high byte to be used as a software interrupt. And so that's why we're passing the 7F here. If you look down in the manual, the interrupts that are actually defined for here are... this talks about the ones we care about. The ones that are... The other ones, like printing and input and stuff, are all here. 7F is the one that we want. It interfaces with the deadbolt to trigger an unlock. The password being correct doesn't matter. Like, it doesn't do any checking. So basically, if we pass 7F as our interrupt and we jump to the hex 10, we should unlock the door. So that's what my shellcode does. We hit assemble, and it's going to spit us out some shellcode. This is conveniently 10 bytes, which will fit right at the end of our payload here. The only problem is we don't know how to jump to it. Typically, the way that this would work, like on what I would do, like on x86 or whatever, if I had an exec stack, is I would look for a jump RSP gadget. I don't see a jump RSP anywhere in here, or a jump SP anywhere in here, and we can tell what jump SP is, or call SP. So jump SP, if we just assemble that, or assemble it, I don't think we're able to do that. It would be RSP. So that's A, which, and I always forget which order this is in. If it's, it looks like this is in big endian or just byte based. So it's possible that we could stick an A somewhere that we can still get to, but there isn't one like just available to us, unfortunately. This also doesn't seem to be relocated. And this is where our username comes from, is in here. But it seems like this all gets overwritten by the time we get to this point. There might be another instruction that we can use rather than like a BRSP. Like we can do a call SP. And the reason I'm saying SP, so stack pointer, if we look at what the stack pointer is pointing to right now, and we can find this just by going to here. It points to basically the beginning of, or the midpoint of our input. SP points to the first byte after our return address. So that's great. If we can like find like a BRSP or a call SP, we would basically be able to jump like directly to our shellcode. We just gotta find that somewhere. We don't have a leak for our stack. We don't know what that is. Conveniently, R14 and R15 both point to 2 bytes before our input. So B776, so 0, 1, 2, 3, 4, 5, 6. This is where those point to, which is said 2 bytes before our input, starting right here. I've been looking for a few different approaches to get to somewhere that we can actually run. I've tried the ROP approach. We can do the shellcode approach. But basically, I haven't really found a good way to get these registers to point to right here. Now, we could jump right here, but like this instruction, this is not consistent. And whatever is here may not be correctly disassembled. So instructions are either 2 bytes or 4 bytes. And so we can't control what's here, and so we can't control what instruction that is. And so in some cases it might be like a NOP effectively, it does nothing. In some cases it might be a 4-byte instruction, which would mean it would take like the first 2 bytes here and fuck up our payload. And we just don't have enough room here because we only have 8 bytes and our shellcode is 10 bytes. So we really need something, either a ROP payload that can fit into the 8 bytes, but we can ignore this, which I haven't really found yet, or we need to find a way to branch to where the stack pointer is. So we can start looking for other ways that we can do a branch to SP. Like a JN0 SP. Now, I don't know. It wants to do a label, and maybe for there's like some special syntax you need. Guess we can look in here. Like these all seem to be like addresses specifically, and maybe you just need to do like a call or a branch in order to go directly to a register, and that's like the difference or something. We can look at MSP 430 instruction set. You can see I've already like searched all through here. Let's see if we can find. There's like a really good just like table that gives us like everything. 2 operand instructions, conditional jumps. I wonder if we could do like R, like maybe we just have to specify it as like R1 or R0 or whatever it ends up being. So like SP, so 0, 1, 2, 3, 4. So it would be like R1. We can see if that works. Yeah, it doesn't like that. And then we'll have all the emulated instructions. Let me see if I can find the actual table that has all like the really useful stuff that I actually want to see. No. Getting closer. I think this is it. Register indirect addressing. Oh, maybe you need to do it that way. Yeah, so this could be it. BR. I don't know why those are different though. It could be like an FF3F maybe. But basically, we just need to find something that we can turn into that gadget. The other thing that's really important about MS-2430, which makes it even more difficult, is that instructions have to be 16-bit aligned. So like we can't jump like typically like on I don't know if ARM lets you do this. Like probably not in Thumb. Maybe it does, or if you're switching between them. But like on Intel, you can arbitrarily like jump into like the middle of another instruction as long as it decodes to something meaningful. So like there's no alignment in here. Like everything is 16-bit aligned, and so I can't like if you try to jump into like the middle here, or like this right here is our branch SP. That ends up giving an error and it just fails. So we can try putting a long enough string in here with our 8 bytes and maybe we can turn that into something useful. I did a bunch of searching in here and like I didn't see like I didn't see anything that like was useful. I don't know why those. Yeah, so our problem is that we can't leak this. We don't know where our stack is. So even if we could put it here, like we can't do anything with it. And then going down here, like we don't see like a 0041. It's just not there, unfortunately. We could try to turn something into that, but doesn't seem like it's going to be super easy. Like this would maybe be a like one possible spot, but like 1, 2, 3, 4, 5, 6. So we can see if we put data here, if we're able to write it ourselves there. We're gonna have to reset this. Oh yeah, no hex characters. 1, 2, 3, 4, 5, 6. So to finish that, and this is our address. We'll continue. It's gonna bring us there. So let's releak this. Let's convert this back. So this is our new base address. Again, we got to go back to disassembly. This isn't really helpful for us to be in our decompilation mode. And yes, I mean we can see that we've already this has already been like wiped out, so we don't have the A's there to even do the use that as an address. That's unfortunate. We can look for other places that might work. I really want to know like what the BR instruction, like why it's emulated. Like how is that different than just a regular jump? I guess that this is more general than the jumps are. The jumps have to go to a label where the BR can be any destination. Same with call. And so in this case, it would be like BRSP, which is 41. Or we could do like call SP, which is 8112. Not something that we have. Unfortunately. Now we could ROP this, but I haven't really had good luck finding the gadgets that we would need. We can look for like a pop R2, but I haven't really seen that. It's an SR, so BIS doesn't set, right? BIS. Oh, it does store it in the destination. So we'd still need to get something in there. That wouldn't really help us. So basically, like, I don't have a ROP gadget finder, so I'm having to like do this all manually. I'm basically looking for everywhere that SR is used, and I'm looking for something that will pop it in there and then return. Oops, that's not what I wanted to do. Let's go with the minimal and and I want something near the bottom of the function because I don't want it to do a whole bunch of other stuff. this is the problem, is that most of the places where there's I guess this is something we could do. And so this is the other problem is so because we only have 10 bytes, there's a lot of these places where we have these add 8 to SP. Now what ends up happening is SP points to our stack, and when you add 8 to it, we're now at the end. This might actually work though. So this SP is pointing to this might be like 2 bytes out of our range. But this is good. We can let's save this. Pop SR add 8 to SP ret. So this is something that's interesting. We can keep this. That's 491E. And then we basically just need to call 10. So we could place this on the stack, and then we just need to have like a call 10, which is right here. I wonder if we could... Oh, no, this is perfect right here. We have a pop SR and then a ret. That's what we want right there. That is the gadget. Uh, 4900. So we can just put our 70 there, and then we just have to call 10, and there's tons of these. I mean, like we can use this one. And I think that this might work, but I'm not 100% sure. FC. And what I'm going to do is I'm going to get the offsets for here. So 4900, 400 minus 49. Basically what I'm doing here is I'm just getting the offset of where these are in the binary, so that I don't have to like bring this like move everything around in whoa, that is not right. Oh, I did plus. I don't have to rebase in binary ninja. So this is 500 hex bytes plus 500, and this is plus 48 FC. For FC. Cool. And so basically we're going to ROP the shellcode instead. So what this ends up looking like is 1, 2, 3, 4, 5, 6, 7, 8. These are our 8 bytes to pad us out to our return address. And then we're going to do our pop SR ret gadget. And then we're going to do 7007F. And then this is our next gadget. So let's reset this. Do that. It's gonna take a second to do all the moving around. %x, and we're gonna hit finish. We've now leaked that. All right. So this is our new base. Plus hex 500. It's 3AC2. And this is all like swapping the bytes because we're a little endian. And then 4FC. 4FC. 36C2. All right. So we can try this. We're going to continue, and we're going to hex encode this. And we're going to send it, and we're going to finish. Wrong password, so C23A is pop SR. If we go down to the stack here, we'll see that our 7F is on the stack. So we're going to pop that. And now it's an SR. And then we're going to ret. And we're going to ret into our next gadget, which is the call 10. And we're in there. And our instruction is unaligned. Why is it unaligned? That is... Somehow we're at PC1, which I don't understand how we got there. But it seems like that is working. Like that is generally like what we want it to be doing. It's possible that the interrupt is not set up properly, and we can go back to here and we can read that. We need to give me software interrupts. All right, so the interrupt kind is passed in R2, the status register on the hide byte. Arguments are passed on the stack. The interrupts are described in detail in section 4. We don't commit memory protection yet. We don't have any. Interrupt 7F. So it seems like this is correct. Now, we may be able to just jump to the int function. I just don't know. Like, it seems like you can just pass 7F to it. I don't know how it's... Is it this one or is it this one? What does this one do? This looks like it's stack-based. Which, you know, would honestly be fine. Is it? Move R15 to R12. SR gets pushed. We could try doing this, and I guess, yeah, we could try just returning into this int and then putting 7f on the stack. That would also potentially work. I think... I think we would want it to actually be here. Let's give this another shot. Let's reset this. I'm also going to come back to this if this doesn't work. And we're going to ban the spammers. Out of here. Let's reset this and let it do its thing. Let's finish. We've got our leak. All right. All right, so we have our base address. We're thinking we're going to return to this. This is at, I gotta grab this. Of course. Just wish it could stay in the dead listing. All right, so it's 4A, 8A. All right, I'm gonna do 2 of these 7Fs because I am not. Oh, actually, it should be this. I believe, because I think that this is what this bis does, is it shifts it. We're gonna see what this does. We can always come back. All right, we're going to finish, and we're set. We're returning into here, and we do that. Push SR. Let's get back to the stack. Push SR, we move R14 to R15. Swap bytes, so it does the magic for us. move R15 to SR. This 8000 hex to SR. That's so weird, but okay. That worked. Okay. That's pretty cool. We got it. So we can go solve this now. That was so much easier than trying to like do some crazy other shit that we were trying. So we'll leak this again. We gotta redo it here, but is it 6-3A6? 6-3A6. And we're gonna rebase this. And we want int, so 2865. We might not actually need this extra one there. Let's try without it, see if it works. If it doesn't, put it back in, and it'll work. Huh, okay, well, we'll try it again. We may actually need it. A2DC. 7F72. That is 5E84. E84 7F00. Cool, we got it. Sweet. I'm curious if that was the intended solution and that's what everyone else is doing. Vladivostok. Let's see what other people did. This is all of them. I don't want to do that. We don't want any spoilers. Let's not look at that. So they did the leak. Yeah, so they did the same thing we did. So cool. We didn't do anything crazy. Let's write this up. This firmware requests a username and password from the user. Username limited to 8 chars. Password limited to 20 chars. Major difference here is that there is ASLR enabled, which shifts both the flash and the stack by a random value. there is a format string vulnerability in the username as it is printed that can be used to leak a reliable flash address. This address is exactly 874 bytes into the flash, which can be used to identify the beginning of flash by subtracting the leaked address (874). The password accepts only 8 bytes are allocated for the password, but 20 bytes are allowed read. We can return directly to the int function. Plus, what is it? Let's just rebase this, I guess, to 4400 so we can get the actual base. Oh, I guess we want to rebase to 0. At 4 EC. For EC. And put 7F step to pass the value to function. This will trigger the deadbolt, unlock the lock. This doesn't actually matter. Username is %x%x. Int address, and then, yep, that's it. Cool. I think we just unlocked Bangalore. I'm guessing this is probably another ASLR level just because it was unlocked by that one. You can check this out. Let's also save this. And we can also get rid of this. And we can save up our backup, or remove our backup. Does this reopen? It does reopen. All right, cool. So we just got to make sure we never do that again. And hopefully request that they add some kind of check to Binary Ninja so that they don't end up overwriting your database if you open a new copy of that file. The lock uses the first MSP430 ever to have memory protection. and it has HSM2. So HSM2, for anyone new, means that the HSM2 will automatically interact with the deadbolt. So there's no code in here that will actually do the unlock. That's fine because we know how to send interrupts now ourselves, and we can just do that. We haven't seen memory protection yet. That is talked about here. Let's see. Memory protection. Some version of the IT Locket Pro contain memory protection, which allow each of the 256 pages to be either executable or writable, but never both. So this is basically the WXOR X protection that you would see on modern processors. This prevents many common attacks. There is an interrupt for Locket Pro, which enables memory protection. There are also interrupts that specify whether a given page should be executable or writable. So most likely what we're going to have to do is use the interrupt to disable the memory protection. We can look here at the list of interrupts. Oh, interesting. So maybe we can't. So it doesn't look like there's a way to turn off dep. Mark as a page as either only executable or only writable. Yeah, so most likely we're probably just going to use a straight up ROP payload here and do a chain because we can't turn dep off, and we can't. I mean, we could theoretically mark individual pages once we've written to them, but it doesn't seem like it's going to be as easy as just writing a ROP chain, assuming we can find the gadgets we need. So my guess is this is probably going to be a pretty simple vulnerability. It seems like maybe we don't have ASLR, which is nice. That's interesting. It's a conditional unlock door. Why would it clear R15 and then return? That's like a no-op. I mean, I guess, yeah, so we could mark pages as executable after we've written to them. It looks like we have a function here, which is pretty nice. And you just pass, I think, your page in R15. And it handles it all for you. We basically need to figure out how pages are passed, if they're just like, and how big pages are. So there's 256 pages, and we have 16-bit address space. So just doing some simple math, 5535 is the number of bytes total. We have 256 pages. So there's 255 bytes per page. Let's make these floats and just make sure that like there's no remainders. Oh, God damn it. That's interesting. Okay, yeah, sorry. It's 200, it's... Well, yeah. So I'm not sure yet if we pass in like a page number or if we pass in like an address. But it seems like uh, every every one of these is a new page. Login. It's just simple puts, get string, puts, set up protection. So it seems like this is all probably called from main. Set up protection. Clear 15. So it marks. So it marks the first page yeah, so it looks like it's sending in pages as numbers, like as like an index, like page 1, page 2, page 3, rather than an address. So we can see how much space we get to read. I'm genuinely curious if it's easier. Oh, the reason why we're gonna want to do this as shellcode and make the stack executable is because we don't have a gadget for calling int. Like we don't have an int function because we're using NitroSM2. So we'd have to like write our own shellcode to basically run the int function that we just used on the previous one, which means it's going to be easier for us to most likely oh, but we don't have it either. It's interesting that there's two rets here. So, yeah, I mean, if we can find a pop SR, which I don't see in here. Yeah, so I'm not seeing any of the gadgets we're gonna need. We probably will have to push this onto the stack, which is fine. We're just going to do some math to figure out like which page it's on, which I think is pretty simple. It looks like we only have one input, which is just like the password. It doesn't ask us for more than that, and it looks like we can write with that 48, 50 bytes of data. Oh, sorry, 30. It is 48. 48 bytes of data, which should be plenty of space for our shellcode. We just gotta see how much space is allocated for our password, and yeah, let's run this. So between 8 and 16. So we probably have 16 characters allocated on the stack for us. Do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Actually, let's 4 right there. I don't want to overwrite the return address so that we can actually see it. Let's finish that out. And let's go to the stack, which is right here. All right. 1, 2, 3, 4. And if we look at login, I think main calls login. Main login. So we're going to be looking for 40, 44 on the stack here, which is right here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Like we thought, we have 16 bytes allocated. So of our 48, 48 minus 16 minus 2 for our return address. We've got 30 bytes to get our ROP payload and then jump to our shellcode. We don't have ASLR, so our stack is going to be consistent, and we're not going to have any problems with it moving around. So our addresses are fine. I don't really care about making a really reliable jump or anything. So we're not going to bother with like the jump SP trick. So here's the one really irritating part, though. So our shellcode is going to potentially, depending how long it is, cross over pages. So you can see here, we're at 3FE0 right here. So 3FEE is the beginning of our input. And this is our return address right here. Right here, this is a new page. If we can fit all of our shellcode in this, it will be ideal, because then we only have to make this one page that we're in right here executable, rather than having to make... I guess we could always just make the one after this executable as well. That's not really like a big deal. We basically need to get a value into R15, and then pass it to make executable, mark page executable. It seems like that's how this works. Yeah. So let's see if we can find a pop R15. We have a pop R11. This is good enough, I think, because oh no, it's not. Damn. I was gonna say it's good enough because we see. Where is that? This right here. It's moving R11 into R15. But I mean, we could always jump to here. But I don't think we actually want to do that. Do we have any other like pop R15s we can use? We've got a R14 to R15. We got some clears. What can we do? If we can get it into R14, we're also fine. But I don't see... anything that gets us into R14, unfortunately. Well, let's figure out what page we're on here. So 3F00 divided by 256. That means it's page 63. So 63S. So 3F. Oh, yeah, that makes sense. Wow, that's dumb of me not to realize that. So we need to get 3F into R15. Is there like a way we can get like some other way we don't have to like pop it or... I guess we could see what the state of the registers are. Maybe there's like something meaningful there that we could use. Maybe we could just turn dep off. Just like, yeah, but I don't want anymore. This is the shitty part. It's like we could take one of these, but... Oh. Yeah. it would keep looping. I wonder if we can get an error message telling us that that it's not executable. We should probably figure that out. So it's 16 bytes and 17. So let's just jump to like EE3F. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. EE3F. Send. So yeah, that should finish. Yeah. So we get the error, so we'll know if it works properly. What's our register state? R13. R13 has it in there. We could always shift that if we can find. I guess we need a gadget though. Yeah, getting like finding the gadgets, especially without like a gadget finder, is definitely like difficult. um, 14 is 10 in it. Like, there's just not a lot of really good gadgets available to us. Like we can get it into R11, but R11 doesn't help us. Unless no, so it doesn't to the protection actually does go symbolic grep. Yeah, I mean the code is so small it's not that bad to like do it by hand. But so we put into R11. We'll run through making everything else. This might be the move is we just let it run its course is we do this. Let's see if this ends up breaking it or if we can just make this work. Where was that pop R11? Right here. All right. All right. I don't remember what challenge this was. Bangalore. So we're gonna do pop R11 Brett. This is at 4508. And then we're gonna do this. 44 F6. And we'll hope that this looping and just turning on dep again isn't that big deal. So 44 F6. So yeah, it's just going to increment from there, basically to make all of everything between the stack and flash executable, which I guess probably isn't such a big deal. Like, it doesn't really affect us. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16. We're going to do our pop 0, 8, 4, 5. We'll have our value, which is 0, 0, 3, F. And then we're going to return into so we have another pop at the end when this finally exits. Which we don't care about. And then we can jump to the stack. So EE 3F. Let's see if this works. So this should get us to the point where we're executing code on the stack. We'll jump back into our shell code here, basically. Come on. Step. Let's finish. So we're gonna pop R11. So we're gonna pop 3F and ret. Oh. Did I do that backwards? Yep, I did. That's wrong. Turn the lights on real quick. All right. And we're going to continue. Oh, we don't want that breakpoint there. So why is it stopping there? All right. Send that. We're going to finish. Let our pop 11. That's correct. And let's go middle mode. So 3, 4. the fuck just happened? Did I? Maybe we don't need this extra. Oh. No, it was... What? Maybe we don't need it. Alright, we're at pop R11. R11 has our value. We return. And we should return now to this loop. Oh, I don't have the address for the next jump, which is the problem. F6 4 and that's the issue. All right. Now we should get all the right stuff. So finish. R11 is correct, and go there. Now we're gonna loop through basically to here. Cannot write to execute only page. Oh. Okay. So we don't do 3F. We do 4O. And then we don't do any of this. That's fine. And then all of our shellcode ends up being back here, which works for me. And I'll do 41414141. Actually, we'll do 4242. We should do 42. At least that way we know it's the right stuff. Continue. Step. Finish. That's not good. So we don't have reliable stack space. Can't move the stack up. why it's lost so much. Like why it's come down here. I wonder if we're gonna have to find like a way to one-shot this to only is there anything in Mark Page executable that we can do? I wonder if we can get it into R14 somehow. Like, maybe we'll get lucky and it just happens to be there or something at the time. $24.65. I mean, I guess we have enough control over it that we could just jump to here. Like, yeah, we have enough control over it. So we push 0, 0 first. And then 3F. Oh. Oh no. That's... Did I jump to the wrong spot? Give me 1 second to retry this real quick. Make sure that this actually is broken before we start going crazy here. Because that was not right. And actually, this is wrong. Yeah, why? Why aren't they like this if it's 4,000? That should be like the correct way to do it. Oh yeah, there we go. This might work. It's just going real slow. I think I just had the numbers wrong. I think this works. Unless we're in an infinite loop. I think it was R11 is... and wrapped around. We're close. It never ends up being here, which is like this always fails. Oh, wait. No. Because it's... Well... Is it... It should be... It's not 4,000. It's... It is 40. Okay, so that's fine. We're gonna redo this, and instead we're gonna set this up with our own thing. So, where was that? We found a different location. We think that executable. All right. There we go. So we are going to jump into write why is it subtracting by 6? Oh, because it's pushing. We're going to jump to right here, I think. So, it's BE44, and then the page we want, which is going to be 3F00. And I guess we do 4.0. And 0.0.0.0. Then, oh no, we do have to do that because it's going to add 10 to the stack pointer. So this is 16, 17, 18, 19, 20, 21, 22. We have enough space. That's all fine. And then we, 10 bytes here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we can just return to like, I don't know, 3F00, and let's see if this works. This might fail because it will push us onto the next page up. Not 100% sure yet. Basically, let's finish that. We're gonna finish that. Stack pointer 3F00. Stack pointer goes to I'm too many bytes. I gotta remove 2 of these. Let's do this. And then we'll return into 3F. Which, this is wrong. This is EE3F. Cannot write to a write-only page. Cannot execute a write-only page. I wonder if it does need to be the other way around. Maybe we're wrong. Am I off by something? Like when this starts, like do we start at 0 or 1? Maybe I'm off by like a 1 or something. Like when this set up protection. It looks like it starts at page 1. Oh no, it starts with page 0. I mean, I could try doing... Yeah, so that's correct. Uh, 3F E. And there should be plenty of bytes there. I can try up one and down one. Maybe I screwed something else up, but it could be off by one. I'm making it executable. Stack is pointing there. Can only execute. I could do 3E. How is it a write-only page? Like we changed it. Like I don't understand. It is the right order. I mean, maybe I'm... Push 0. Push R14, so that should be right. Yeah, cannot execute write-only page. That's so strange. Move 91. And 91 is our interrupt. Oh, it's not. Maybe the value we're giving it is bad. What is turning on dep is 90. interesting. I don't know why. So it's listed as 91 here, 90, 91. Is that, I mean, there's something weird about 91? So it's that's 9 and 1. Why? I wonder if they changed it or something. Eight thousand is put char. That's 0. Are they masking off something? Yeah, I mean, they must be masking something off because everything... It's at 10. That is strange. Let's see what's getting passed into here. R15. Step. 44, which is right here. It's what we expect. Oh. I see. We do need the 6 bytes. That explains it. All right. So we can do this. We'll do 3F. E3F. And after, it's going to push it down 16 bytes from here. So that's 2, 4, 6, 8, 10, 11, 12, 13, 14. That's all still correct. Okay. I think PC is at 41401, which we might be too many off now. Or let's see. Why does it think that? So we're one off. We more than one off? Oh, yeah. So we don't need these. It must just push the stack further, I guess. We thought. FEE, and it's gonna execute that. It worked. Okay, so we just need some shellcode now. This. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this, I think the shellcode didn't work. And it might be because we need to fix this value. Because all of these seem to be like starting at like 8, 0. So 8, 0 plus that. We can try this. And we can try moving it up. Yeah, so it's at 0. Something's wrong here. Yeah, we're off. finish, step. Yeah, so that's the wrong value. But we can say 7f plus just ff. Okay, that's fine. ff. Cool, that worked. Let's do the solve. We got it. All right. So I don't know why the documentation is wrong. It's not actually 0, 0. It's 8, 0 plus that. But whatever, it works. We know. Let's document this real quick. We don't need any of that. Bangalore introduces write XOR execute. Or execute, but never both. Is an overflow in the password at 16 bytes was us to hijack control flow using ROP. Turn into the what function was that? It was mark page executable. Function and specify our own values on the stack to set the page where our input starts as executable. Put shellcode at the beginning, and then return to the shellcode. And then our stuff is basically this. I don't know why it doesn't think that there's a I don't know. Sweet. So I think I'm gonna wrap up for the night. Made a lot of good progress today. We got Vladivostok done and Bangalore. Lagos, I'm not exactly sure what this is yet. I guess we can look real quick. Only alphanumeric. So we're gonna need alphanumeric shellcode on this one, which means we probably have to write some like really creative shellcode. Probably pretty straightforward of an overflow, and like, I mean, yeah. How much of this? I guess we don't have our assembler here, but. It's like this is alphanumeric. Some of this is not alphanumeric, but I mean, like we can build alphanumeric for a lot of this stuff. I'm not sure how we're gonna do the call, but maybe like we can find a return address. AA is not. This is alphanumeric right here. And so I think we're just gonna end up having to like build a bit of an interesting ROP chain. But yeah, this shouldn't be too bad. Anyway, have a good night, everyone. Have a good Christmas. Might pick this up tomorrow and try to wrap it up. It looks like we have how many left? Hall of Fame. Like, there's 3 left. Lagos, South America, one we just saw, and then 2 more. These look like they're hard. Maybe they're just culminations of everything, but either way, maybe tomorrow or Sunday, we'll take a crack at Lagos and see how far we can get. I don't expect this to be too hard. It's mostly going to be us writing complicated shellcode more than anything else. But as I said, have a good Christmas, everyone. Enjoy the night, and we'll be back soon. Good night, everyone.